Math 1314, Tyler Junior College, section 3.5, rational functions, identifying vertical asymptotes, more examples. At the end of the last video, which went longer than I expected, I kind of regretted the fact that we didn't do more examples, so we're just going to do a quick video with 3 examples of identifying vertical asymptotes and holes in graph. Recall that we start by solving the denominator equal to 0, then reducing the fraction if possible, and seeing if those solutions make the reduced function undefined or not. So let's start with A, f of x equals x plus 3 over x minus 1. Step number 1, solve the denominator equal to 0. That's easy, that gives us x equals 1. Step number 2, if possible, factor and cancel. This will not. This will not factor and cancel, so the function will not reduce. I can't cancel the x's, you can only cancel parts of multiplication problems in a fraction. So there is no reduced function. Or you could say that it is its own reduced function. So in other words, you could say that the reduced function is the original. No reduction happened. It doesn't change what happens next. So we check the quote-unquote reduced function at the solution to 1, but it didn't change, so this is undefined. What does that mean? Undefined in the reduced function means that you are a vertical asymptote. So there's a vertical asymptote at x equals 1, and there are no holes. For part B, g of x equals 5x plus 10 over x squared minus 4. By the way, you can always pause and try problems on your own, even if I don't say, now's a good time to pause and try to work this. But you might want to on this one. For g of x, same steps. Start by solving the denominator equal to 0. X squared minus 4 equals 0. If you solve that, you'll get x equals plus or minus 2. Second step, try to reduce this function by factoring and canceling. The 5x plus 10 has a common factor of 5, which would leave another factor of x plus 2. Of course, the denominator is x plus 2 and x minus 2. The x plus 2's cancel. That leaves 5 over x minus 2 is the reduced function. Now, there are some professors that will say every canceled factor makes a hole in the graph. That is not true. A canceled factor might make a hole in the graph, as you'll see in the next example. But let's continue. Our reduced function is 5 over x minus 2 because the common factors of x plus 2 canceled. So now, to pass judgment on which of these numbers are vertical asymptotes and which are holes in the graph, we need to evaluate the reduced function at both. So gr of 2 and gr of negative 2. If we substitute 2 into this function, it will be undefined, 5 divided by 0. However, if we substitute negative 2 into the reduced function, we'll get 5 on top, negative 4 on the bottom, and so we get negative 5/4. So our conclusions is there's a vertical asymptote at x equals 2, because it was still undefined in the reduced function. But now we know there's a hole, and we know exactly where it's at. It's at negative 2, 5/4. So if we were sketching this, we would draw the graph of this, but stick a hole in it. In fact, that's how we're going to graph these. We're going to reduce them, graph that, and then put the holes where they belong. Let's take a look at C. H of x equals, oh, look at this mess. But the good news is this mess is already factored. I don't want factoring to be an impediment on this one. It's not impossible to foil these out and see if they're factorable. We have techniques that we learned in previous videos to do that. But I wanted the solving and the canceling to be easy. Solving the denominator equal to 0 is actually pretty easy because it's already factored. And when you're solving something that is factored and equal to 0, you just have to put each individual factor equal to 0 and solve it. So we would get x is equal to 1, and x is equal to negative 1. So x equals plus or minus 1. Those are the numbers that would be excluded from the Those are the numbers that can be vertical asymptotes or holes. Next, reduce the function. Well, the reducing is kind of easy because it's already factored. So let's just think about what the reduced function would be. HR of x. For the x minus 1s, there's one factor on top and two on the bottom. So you could cancel one of them. So the one on the top would disappear and we'd be left with an x minus 1 on the bottom. Does it need to be in parentheses? If there's something else down there, but there won't be. Because on the x plus 1s, they match, but there's two on the top and one on the bottom. So the x plus 1 on the bottom would cancel one of the x plus 1s on the top and leave an x plus 1 on the top. So in this case, we had a cancellation with both factors. One of them canceled there, leaving one on the bottom. One of them canceled here, leaving one on top. But they're not both holes. To determine which is which, we need to evaluate the reduced function at the solutions we got in step 1. So we need to evaluate at 1, and we need to evaluate at negative 1. 1 still makes it undefined because there's still an x minus 1 down here. But negative 1 will actually work because if you substitute negative 1, you get negative 1 plus 1 on top, which is 0. Negative 1 minus 1 on the bottom, which is negative 2. 0 divided by 2 is 0. So, there's a vertical asymptote at x equals 1, but there's a hole at negative 1, comma 0. Even though both factors had some canceling. So, canceled factors doesn't mean hole in graph. Canceled factors means you may be a hole or you may be a vertical asymptote. But if there are no canceled factors like over here, then everything that you find is a vertical asymptote. You don't have to check. There is a way to state whether you're a vertical asymptote versus a hole in terms of multiplicity. For example, 1 was a multiplicity of the denominator, 1 was a 0 of the denominator of multiplicity 2, but 1 was a 0 of the numerator of multiplicity 1. So if you want the super technical description, a 0 of the denominator is a vertical asymptote if its multiplicity is greater in the denominator than the numerator, but a 0 of the denominator is a hole if the multiplicity is greater in the numerator than the denominator. Basically saying, where's it going to be left over after you're done canceling? All right, so vertical asymptotes aren't that hard to find. Every once in a while, one of them pretends that they're a vertical asymptote, but they're actually a hole in the graph.